conservative vector fields. Given f equals 2x ln of y, comma, x squared over y plus z squared, comma, 2yz, find the potential function. And a lot of times in this book they call it little f. So let's find little f, the potential function. So first what we need to do is think about what the potential function is. So when I think of vector fields, the gradient of f, which is the potential function here, equals f. So if I look at this function here, or this vector field here, this PQR here that we see, what we can think of when we think of the gradient function is f of x, f of y, f of z. And that's what the gradient of f would be, which this equals my f here. So what's happening here is my f of x, or my fx, equals 2x ln y. So when I take the partial derivative of f with respect to x, I get 2x ln of y. And when I take that same function f, the derivative of that with respect to y, I get x squared over y plus z squared. And when I take the derivative, that same function f with respect to z, I get 2yz. So what that means here is if I'm differentiating to get my vector field, I'm going to integrate to get my little f back, or my potential function, which is my potential function. So I'm going to take the integral of 2x ln y, and since that's my first component here, that should be my derivative of f with respect to x. So I'm going to do the integral with respect to x and get that answer. So this is going to be x squared ln y. Now ln of y doesn't serve a purpose here because it's just a constant, and this is with respect to x. So my variable is 2x, which turns out to be x squared ln of y plus c. Okay, now what we're going to do is we're just going to do that same thing with the rest of these. So for the second one, that's the integral of x squared over y plus z squared. So now, and that's going to be dy, because that's my fy when I differentiate it. So I'm going to integrate this middle term, x squared over y plus z squared, with respect to dy. Okay, so here it is. So we're going to do this now. So I'm going to rewrite it a little differently here. And this might help the integral for you guys. Actually, it doesn't. Maybe this way, though. And hopefully you see that the integral of 1 over y equals ln of y. And remember, the x squared is just going along for the ride. So that's going to give me x squared ln of y plus z squared y. Because this is just like a constant. Like if that was 3, the integral at 3 with respect to dy would be 3y. So this is just going to be z squared y plus c. Now we're going to do the last one here. So the last one's going to be 2yz. Now again, that's for my fz. So since I differentiated to get 2yz, when I differentiated with respect to z there, then that tells me this is going to be the integral of dz with respect to z. Okay, so then this is going to equal yz squared, because that 2 is going to go up to my power, and then it's just going to be yz squared plus c. Now, the way we look at this is we just kind of think about this all together. So now, remember, we're trying to think of a function here that when I take it with respect to x, I get 2x ln of y. When I take that same function with respect to y, I get x squared over y plus z squared. And when I take that same function with respect to z, I get 2yz. So I'm looking at all of these components here. So let's see which ones are different. So this one here, actually let's look at the same first, is the same as this one here, and I don't have any more of those. So you know what that tells me? That tells me there I'm going to have all of those at least once. And again, I count them only once. Oops, leave the plus C for later. Okay, now the next one then is, let's see if there's any other different ones. So I did that one. There's a different one there. And this one's the same as that one. Okay, it's just switched around, but they are the same. So that's going to be plus yz squared. I'm just going to write it that way. And there's nothing new other than those two. So then I would say plus C. Now what we're going to do here is we're going to test this. I want you to see this all together here because it almost seemed too easy to do. I know it did. I just integrated and I got what I got and just matched up things. Things were the same, I put it down. If they weren't the same, I just put them in there. And again with plus or minus. All right, so now taking a look at this, what we're going to do is we're just going to take the partials of this because I want you to see what happens here. So I'm going to take this f here with respect to x. So for this first piece here, it's going to be 2x ln y, and then there's no other x's, so that would go to 0, that would go to 0. So if I look above, notice my fx. That is my fx there. Okay, now let's look at fy. So then the ln of y of the first piece is going to be 1 over y, so it's x squared over y. And then for the second piece, I'm just going to get plus z squared. And if I look at my fy, which is here, and I look at what it goes to there, it gives me exactly that piece. So now let's do f of z. So now that's 0. Okay, and then this is going to be 2x or 2yz, excuse me. And if I look above here for the 2yz, there's my f of z. And when I look at that, notice it's the same thing. So it just goes to show you that, yes, it is that simple. Once I find it, yes, it matches up. That's all I really have to do for those. And it works out. So there's my answer. Now this section is talking about conservative vector fields specifically. So that's why when I wrote this vector field out here, I have a potential function. Now, if it's a conservative vector field, it has a potential function. So I was certain that it had a potential function in this section. So keep that in mind too, that if I'm dealing with a conservative vector field, it will have a potential function.